So the title for these, just to make it fun, are the college party problems. So you got to do something to get y'all to at least try to listen. College party problems. Here we go. Problem number one is going to involve the ladder. And what's basically the ladder? How do you spell ladder? L-A-D? Two D's?
Yes, sir.
The ladder. Okay, the ladder. And what you do at college is you got the guy up on top of the 25-foot ladder, all right? Which that's pretty far up there. You know, 25 feet, yeah, that's a little bit scary being up that high. And you start moving the bottom of the ladder away from the wall while he's up there. And you see if he squeals or, you know, starts screaming in fear of falling. Because what's going to happen is you move the ladder out, the top's going to come out from under him, right? So what we're going to do is we're going to pull that ladder out. And here's what I want to show you about it. When I pull the ladder out a foot, I want y'all to think and watch what happens at the top of the ladder. Because I want to dispel something that students just think. And, you know, a lot of people think this. If I pull the bottom out 1 foot, notice how far the top goes down? It didn't go down a whole foot, right? So it's not going to scare him as much as you might think when you pull that ladder out a foot. Because if you pull it out a foot here, he does not drop a foot up there. Okay? Now, if you draw it out another foot, it might scare him a little bit more now that you're further from the wall at the base, because all of a sudden it doesn't drop. Notice now, for the first foot it dropped that much, right? But for the second foot it what? Dropped that much. So if you were pulling this out, that might scare him a little bit more because it dropped a little bit more, right? Okay, that might create problems. Now, if you move it out again 1 foot, like so, now it's dropping a lot. I mean, it dropped quite a bit there. It dropped from there to there. See? So just because you move it 1 foot at the bottom does not mean it's going to move 1 foot at the top. And you know, it's just how life is. It's just, you know, I'm showing you, because I've had students in the past go, oh, well, I just think it has to move 1 foot at the top. It doesn't, okay? It doesn't do that. Now, if you move it another foot here, it moves quite a ways now. And if you move it another foot, it will move all the way down to about right there. Okay? All the way here, pretty much. So, and there it looks like, you know, it's almost a foot for a foot, right? But the catch is the top of the ladder is not moving at the same speed as the bottom of it. Because I could have said I moved those out 1 foot per second. So it moved that far the first second, that far the second second, that far the third second, right? If it was 1 foot per second. And we can't move it that fast and explain it. There's your ladder. Now, so we take a ladder and we're going to draw the problem out. We're going to put a ladder against the wall, and we're going to make our ladder 25 feet instead of whatever this is, a little over 6. Okay. We're going to take a 25-foot ladder and we're going to put it against the wall. Okay, here's our wall, and when I draw these out, I'm going to tell you some little steps that you want to take in working these. I'm going to tell you some pitfalls to avoid. Right angle there, and my 25-foot ladder. And I'm going to try to make my ladder a little better than I did yesterday. Okay, 25 feet. Okay, 25 feet. I'm going to pull the base of the ladder out at 2 feet per second. I'm going to pull the base out at 2 feet per second. In other words, I'm going to move this way 2 feet per second. I notice we use 1 foot there, but what I want to do is use 2 feet because I want a number that you can see following it through the problem. All right. Now, when I talk about the top of the ladder moving down, I've got to talk about at specific moments moving down. Right? Because does it move down at the same speed the whole time? No. Even though I'm moving it out at the same speed the whole time, it doesn't fall or slide down the wall at the same speed the whole time. So what we're going to do is we're going to say, how fast is top of ladder sliding down when base is 7 feet from wall. All right? We'll talk about a specific moment when the base is 7 feet from the wall. Now, you could call this A and call this B, or you can call this X and you can call this Y. I kind of want to call them X and Y, but if you want to, you could make this B and you can make that A. Doesn't matter. But here's the catch. Don't put 7 right there. Don't put anything on this drawing that's changing. If it's something that's changing, it has to be a variable on this drawing. All right? If it's changing, it must be a variable. If you're not sure if it's a variable or not, like the 25, if you were to put C there or Z or something, you'd be okay. But since 25 is constant, we'll go ahead and put it on the drawing. All right, I'm going to call the base X here. We'll call this Y. And the first step to this, I guess what we could tell you too is, see the 2 feet per second right there? That's really the change in X with respect to time. That's what it equals. If X is that side, then the change in X with respect to time is 2 feet per second. And what you're really looking for up here is the change in Y with respect to time. That's what you're really looking for. Except you're not looking for it all the time, you're looking for it at what? One specific moment. So when you write your question over here, put, and always write this with these, do like this. dy over dt equals question mark at x equals 7 feet. Okay? Or at 7 feet. The reason why is because when you find this value, you're not finding it for everywhere. You're just finding it for what? When x equals what? 7 feet. And by writing this statement, you will make your life a lot easier for following along. Okay. What formula relates the x, the y, and the 25?
X squared plus y squared equals 25 squared.
X squared plus y squared equals 25 squared. Okay, that's the related part of this story. That relates it. One of the things you're going to be doing when you work these is you're always going to be looking for formulas that relate the parts. All right? Anytime you have a right triangle, guess what probably is going to relate the parts? Pythagoras. Okay? He's going to relate the parts. But the problem is, you need to turn that into a rate formula. Okay? Rate. And here's the good news. Because of calculus, we do not have to turn those into equations in terms of time. Okay? You'd have, and then do a bunch of nasty work. What we're going to do, since we know about implicit functions, would y'all agree x is a function of time? Would y'all okay that y is a function of time? We're going to take the derivative of it with respect to time. 2x dx over dt plus 2y dy over dt equals 0. Now, if you would have put a c here, you would have still got 0 eventually, because what's the change in c? 0. If you'd have put a c there, you'd have got 2c, change in c with respect to time, 2 times 25, but what is the change in it? It's always going to be what? 25. So there's your 0, and there's your 0. All right? So, but if you would have put 7 here, you've got a big 0 there, right? We're not in Mr. Rumble's room, so it can't be the ghost. The ghost lives on the 3rd floor, don't worry. That's just gravity.
Mr. Rumble was.
Yeah, the ghost is on the 3rd floor. Y'all know that's the ghost room, right? Don't be here long enough. The ghost does not hang out down in the catacombs. All right, once I get to this step, I just start putting numbers in there. I hate to admit it, but it's true. I know I can divide out the 2's, and I know what the x value is. What is the x value? The x value is 7. The change in x is 2. I know that. The y value I don't know yet, and I'm also looking for the change in y. Equals 0. Let's find the y value. Do not work it out on that picture, because you don't want to put the 7 on this picture, right? We're not putting the 7 on that picture. But what we can do is over here on the side of the page, we can go, 25, 7. So how long is that side? I used a triple because I didn't want to do any work. 24. Okay, that's one of your triples. 7, 24, 25. So the y value is what? 24. So I put the y value in there, and then I simply work it out. Now, Mr. Goebel would not like the way I do this, because I think he puts units in everything. And I guess if I was in a physics class, I'd have to do that, because my teacher would want it. I'll be honest, I already know it's going to be feet per second, and I'm doing everything in feet and seconds. So I'm not going to sit there and put feet and divide them all out. I'm lazy. Of course, that's the reason I ended up in front of you today. Somebody said there's supposed to be a DT there, Mr. Evans. You changed it while you were writing. And I get negative 7 over 12. Negative 7 over 12 feet per second. Don't throw the negative sign away. Keep that negative sign around. All right? Negative 7, 12 feet per second. So it moved about a half a foot. Moved 7 inches. 7 twelfths per foot, moved 7 inches. Or it'd be moving at 7 inches in that second. That's pretty quick. That would scare me, drop that fast. You know, 25, well, you wouldn't be 25 feet up. I did 7, I got 14. Brought it over here, made it negative 14. Right? And then I divided by 24, and then I reduced it. I did the little algebra steps there and got it down to that. Now, any question on the process up to here? Because we got to talk about this negative sign. I need all your attention when we get to it. Yes, ma'am.
Okay, in the problem, like the word problem part, how did you know not to put 7 on the picture?
Okay, if that is sliding down, and I'm pulling that away from the wall, is it always going to be 7 down there?
No, sure.
There you go. That's how I know. Is that tip always going to be 24 feet high?
No.
No, don't put it on this picture. There you go.
Whenever it's not a Pythagorean triple, how do you know what number?
Oh, you got to work it out using the Pythagorean theorem. You'll get a radical. Yeah. You got to.
How do you solve it without x or y?
Put them right here. You're gonna have to know one of them in order to get the other one.
So you can just pick whichever one.
Well, I told you in the problem
Oh,
when the base is 7 feet.
Okay.
Now, If I worked it again, I said when the base is only 3 feet out, you'd have to put a 3 here, and then you'd have to find that value, right? But why am I not putting the 3 over there? Because I don't want anything on that one that's going to mess up my concept. This is only at a what? Moment. Yeah, this is at a moment. Let's write that. At a moment. And you can change that moment. You can say, hey, let's do it for when the base is 10 feet away. Something like that. Okay? Now, let's talk about the -7. Why did you get a negative value here?
Because you're going down.
Okay, because you're going down. You can already tell I don't like that answer quite perfect. What did you say?
Because it's moving away from the wall.
This is moving away from the wall, and it's positive. This is moving down the wall.
Is that
Okay.
do something with like deceleration or something?
No.
Okay.
Okay, Miss Mary.
Last name is Taylor. Is it, are you have the last name or first?
First name, so I can just
Anna Claire.
Anna Claire. Anna Claire said because it's falling. Well, okay, the reason we would say it was negative if it was falling is because it's getting closer to the ground. So the distance from the ground is getting what? Smaller. Okay? When you see a negative change like that, that means the y value itself is getting smaller. All right? dy over dt is a negative. That means the y is getting what? Smaller. Okay? So that way, if you had it, it could be at an angle like this, and it could be getting what? Smaller. Then your rate's going to be a negative. If it's getting longer, then your rate's going to be a what? Positive. Okay? Now, when you look at final answers in the textbooks and all that, they don't put the negative sign on there because we just said how fast. All right? Speed, absolute value. But what I'm going to tell you is when you're working the problems, you need to keep that negative sign there. All right? Keep the negative sign there. All right. That's part A. We scared the guy at the top of the ladder. Guy at the top of the ladder gets scared. He's looking down. And that's step 1. Now, from there, we're going to keep that number. We need that number, that -7/12. But what I want to do is add some steps to this or add some information to it. Let's go ahead and look at just a simple geometry type situation. See this triangle right here? I want to know the change in the area with respect to time equals question when x equals 7 feet. We'll go add another question. I want to know the change in that area of that triangle. Because if you watch me slide that down the wall, you realize that the area was really small. That area, right? Got larger, larger, and then eventually the area started getting what again? Started getting small again. Is that okay? If not, I've got this to help wake you up. Now, what formula would relate all the x and y in area together? Just the plain old what? Area formula. Okay, anytime you start talking about changes in area, changes in volume, or anything like that, you're going to use the formula for what you're asking. Yeah, I'm looking to see how much room I got over here on the side board so I can finish writing over there. Yeah, oh, zoom it that way. Okay, got the triangle right there you need. Here we go. We need, if we're going to talk about change in area, we need the area formula. What is the area formula for that triangle?
1/2 base times height.
And what's the base?
X.
X. What's the height?
Y.
Y. Do not put a 7 or a 24 there because those are what? Changing. Now, there's your related part. We're going to do the rate part. How do you turn any related problem into a rate problem? You take the
Derivative.
derivative. Now, I'm gonna pick on, yes ma'am?
How does, like, finding the slope of a tangent line, like, go into the rate?
All right. If you look at the slope of the tangent line, it's the rate at that one point right there, because it's measuring, okay, I'm measuring this being a timeline this way, and this being the amount of y.
Okay.
Okay? So then it's taking the change in y with respect to change in time.
Yes, sir.
Is
Okay.
that cool? Yeah.
Mhm.
And that, yeah, you're back to that slope of the tangent is a rate.
Mhm.
All right. Now, when you take the derivative of this, and I'm going to be kind of mean here, because no, I'm not, because I want to know if Captain Tree's kids would know this. You do realize that that is a product rule right there, right? Everybody see product rule happening? Okay. So, we take the derivative with respect to time. 1/2 dx over dt times the y plus 1/2 x dy over dt. Then we just start gathering up the information from the problem. Because we're still talking about when x equals how much? 7. So we go dA over dt equals 1/2. We know the change in x is 2. We know the y value right now is how much? 24. We know the x value is 7, and this is where it's real important. The y side is getting shorter, isn't it? You better put a -7/12 there. If you put a +7/12 out on the end, you're saying that both sides are getting longer. Well, that's going to be a different change in area than if one side's getting longer and one side's getting shorter. Is that all right? So see, that's the reason that negative sign is so important. Because if you don't put that negative sign out there, you're telling me that the ladder would have to be getting longer too, right? But you're telling me this side would be getting longer and this side would be getting longer, and that would make your change in area different than if one's getting shorter and one's getting longer. So far, so good. You work that out. I don't, you can figure it out. Change in area with respect to time equals 24 minus 49 over 24. And that's going to be what? Feet squared per second. It's an area, so it's going to be square feet. You can get a common denominator, put those together. All right? 24 times 24, 144 times 4. And then minus 49. A bunch of little stuff. Okay. And that's the change in area. So when you're looking at these problems, they talk about changes in volume, changes in surface area, all that kind of stuff. You're going to need to know those geometric formulas. All right? Now, we're going to do one more thing with the ladder. We're trying to see if the kid, the person you met at the party is smart enough to spend any more time with, so you have to ask them a question about the ladder. Gosh, that would be a bad way. Oh, I don't know. It is true, though. If somebody's not intelligent, you're not going to want to hang around with them very long, right? Okay? They may have a good heart, and that's because you want to hang around, but let's be honest. Somebody better be intelligent, or you're not going to want to hang around that long. Here we go. Now, the third question. See this angle? The third question. To do the third question, I'm going to fit it right in here, and I'm going to erase these first two questions. All right? The third question, of course, is how fast is that angle changing? Yeah, how fast is that angle changing? And I'm gonna leave this picture over here because we might need it. What is the change in the angle between the ladder and the floor rate when x equals 7? We're still going to use the 7 feet because we've already worked so much of this. And I'm going to help you out with this. You must use trig if you're looking for the change in angle or if you know the change in angle. If you're given a change in angle or you're looking for a change in angle, you're going to have to use trig, folks. All right? It's just that simple. You've got to use trig. Now, there's other times to use trig that makes it helpful, but that's when you must use trig. What trig function would relate either the x and the 25, the y and the 25, or it's got to relate theta with x and 25, or y and 25, or y over x. What trig function could do that?
Sine.
Sine. Sine would make it what? Y over 25. And since we already know the change in y and everything, that would be good. But if they didn't tell us to already find the change in y, might be better to use which one? Cosine, because we already know x and we already know what? Change in x. I would use cosine. If you use sine, still going to work. If you use tangent, it's still going to work, except you're going to have to take the derivative of what? Y over x. And if you take the derivative of y over x, you've got to use the what? Quotient rule. See why I'm avoiding that one? So let's do cosine. Cosine of theta equals x over 25. And I take the derivative with respect to time. I get negative sine theta. D theta over dt. Don't forget, derivative of cosine u is negative sine u, but then you got to take the derivative of the u. Then when you take the derivative of the other side, I like to write it 1 over 25 dx over dt, because I wrote that as 1 over 25 times x before I took the derivative. It just makes it look a little bit easier. Somebody says, well, all I got to do now is substitute numbers in there. That's right. All you got to do is substitute numbers in there. You know the dx over dt, how much is it? 2. X is 7, but dx over dt is what? 2. Now, we're looking for d theta, right? So we'll just put that right here. And then I'm going to put my negative sign, and then I'm going to talk to you about finding sine theta. And I want your attention on this one, because I do not want you to look bad in college. I do not want Daddy Butler tapping on your desk, laughing at you. Okay? I don't want to ridicule you. Folks, you do not need a calculator to find out what the sine of theta equals at this moment. And if you had a calculator to do it, you're just wasting your time. All right? I mean, it'll work, but you're going to get a number that's not a perfect exact number. Folks, see this right here? See this? This is the moment that's 7, right? And the moment this is 7, this is how much? 24, and that's what? 25, right? I'm going to put my little theta in there. Tell me what the sine of theta equals.
24 over 25.
4 over 25. All you got to do is look at your triangle and it tells you the sine. Reference triangles that you talked about last year, and we kept telling you, you've got to know these reference triangles, you've got to know how to set up the triangles to make all your sines and cosines. That's it.